And that's I could put three words together, and that's about as far as I could do. So I apologize for the title. And the idea was if Kevin was going to talk to you about making elements, I thought I'd talk about the rest of what goes on in a star and the sun and what will happen to the sun and why it happens to the sun, because I don't really care what happens to the sun. But it could be what I'm curious about why it happens to the sun. So right now we're in a good place with the sun. The sun is bright. It's got a ridiculous number of watts coming out of it. We're 93 million miles away, but it has got 4 times 10 to 26 watts of power coming out of it. Who cares what that number is? It warms the Earth. And we're living on the Earth. It's nice. The Earth is habitable. We're in a habitable zone, and I'm very proud of this little diagram I made here because it actually shows something that it's about right to scale. The sun's size, as you see it there, is about right. That's how big the sun is. It is very bright, but that's how big the sun is. And you see the orbits and I've labeled them very carefully, and they've gone off the screen. Not my computer, so not my fault. These guys said it was going to be perfect.
Whoa. So in the instructions it said watch the edit.
Mercury, Venus, Earth, Mars orbit, and that's where we are habitable. And we are just within the habitable zone. That's why we're living. If we weren't there, we would not be living. Okay, but as my captain says, it will not always be this way. And why is that? Well, you had a little bit of physics from Kevin, and it's basically the same physics. The sun it's a big ball of gas. It's gas. It's the same gas like in the atmosphere here. So what holds it up? Gravity. Everything has mass, and everything wants to be pulled down. So why shouldn't the material on the top of the sun just be pulled down, squish, down to a black hole? It's gravity pulling it down. What's holding it up? And what's holding it up is the same thing that holds your car tire up, your bicycle tire up. It's the pressure of gas. Atoms moving about.
Turns out I need it.
Banging about. Move. Bang. Exerting pressure. Bang. And it balances gravity. It better, or else the sun, if it didn't, the sun would go squish. So, we're fine. And so what is this, and there's a nice balance. So what does the balance depend on? Well, it's these particles, these gas particles banging about. Fine, but what does that depend on? Well, clearly, more atoms, more banging, more pressure, more push. Take away half the atoms, you're not going to have that much, you're going to have less push, less holding you up. Temperature. Kevin described temperature, how fast things are moving. The faster they're moving, the bigger the bangs, the bigger the push. You change the temperature, you get more of a push. Either one changes. If you decrease either one, gravity is going to win. But you don't want the sun to collapse or anything, so there's always going to have to be a balance. Balance must be maintained. So, as you learned from Kevin, all the nuclear reactions, all the actions in the sun happened in the inner 15% or so, the core. That's where all the action is, all the nuclear fusion is. That's where people, if you want to learn about what's going on, that's what you talk about. What about the rest of the sun? It's just sitting there, doing nothing, providing weight for the center of the sun, just sitting on top of it. but it's not doing anything. It's just sitting there. The inside, in the very core, you have nuclear reactions. Nuclear reactions make the energy, and the energy makes its way out. Now, it can take a little bit of time for the energy to make its way out. If the energy is produced and it goes boingy, 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 boingy around until eventually it gets out. It gets out pretty quickly, only 10 million years or so. After 10 million years, the energy that's produced today actually makes its way out to the top of the sun. And we can see. You turn off nuclear reactions in the sun right now, snap of a finger. Well, in 10 million years, we're going to find out about it, at least from the energy standpoint. So,
is that pathway an art of conception, or is that based on it?
It's basically a random walk. That's all it is. The drunkard's walk. And as far as where you get that, you Google it. Everything you find here, you can just Google. Yeah, it's a photon making its way out. After all, never make anything when you can steal it. Okay. So there's fusion in the center of the sun. Very good. It makes energy. Very good. 4 hydrogens get fused to 1 helium. Very good. But you're losing particles. Every time you fuse, you've taken 4 particles and made them into 1 particle. That's fewer particles moving around. We just said what pressure depends on. Depends on temperature and depends on how many particles are moving around. Well, now you have fewer particles moving around. How do you maintain balance? Well, if you're going to have fewer particles moving around, you better have a higher temperature to compensate. So the temperature goes up. The temperature goes up, more fusions occur. More fusions occur, more light is produced. So, just because of this, the sun becomes hotter and brighter. The sun, over the years, has been gradually getting brighter and brighter. Long time ago, it was maybe only 75% as bright as it is now. In the future, it will be brighter yet. Well, what happens if you make the sun brighter? What happens to the habitable zone? Well, in about, come on, you can do it. In about 2 billion years or so, bye-bye Earth. Move out to Mars. As you see, the politicians must be preparing for that right now. It is important. You know they've already had their lobotomies to get them to get elected in the first place, so that they can start thinking about this problem. Okay, so we've got a couple billion years, but the sun is not going to change a whole lot, just get bright enough to kill us. All right, either that or remove. Then what happens? Well, just because it's bright enough to kill us doesn't mean it won't stop fusing, and it will just keep on fusing, converting more hydrogen to helium in the core, with the rest of the star just sitting there doing nothing. The rest of the sun just sits there doing nothing. Eventually, though, the hydrogen runs out in the core. There's no more. No more energy in the core. Nothing to support the core. The core starts to collapse. Kevin talked a little bit about that. But there's right outside the core, just outside, a few steps away, there's plenty of stuff. There's plenty of hydrogen. So the hydrogen actually starts to fuse in a little shell right around the core, because that's where the hydrogen is. There isn't any hydrogen in the core. There's hydrogen in a little shell around the core. All right, that's fine. And when that happens, it's not extraordinarily bright. It's pretty bright, but not extraordinarily bright, in at least the energy being produced in the shell. But it starts off the catastrophe. Oh, what catastrophe is that? Fun fact. There's energy being produced in the sun, and the energy is percolating out. I said it takes 10 million years. It really turns out, though, that energy moves through material in the sun easier when the material is hot. When the material goes cooler, the energy has a harder time to get through. Here's a scientific plot. It actually has numbers and things like that in obscure units, showing that as the temperature drops from 30 million degrees down, it's getting harder and harder and harder for the energy to make its way out. All right. It still does make its way out, but it's harder. It just takes longer to push through. That random walk takes a longer time. What does that mean? This energy can get dammed up. So, let's go through what it means. It's a very simple little argument. Hydrogen starts to fuse in a little shell. Hydrogen fusion, that's like a nuclear bomb. Boom. Instead of being in the center, it's out here. And the material right around it has to be affected by that. There's an explosion. The material is pushed out. Or radiation pressure, it's whatever you want. But the material here is pushed out a little bit by the shell burning. All right? Material pushed out. Good. It's further away from the core. It's further away from the core, further away from the shell. It's further away from the stove.
Oh yeah, I would definitely let you guys.
It starts to cool.
Alright, see.
Starts to cool. The energy going through that gets dammed up. It can't make it through as easy. It sticks around. It's sort of stuck. And the energy has to do something there while it's stuck. It has to do something. So the energy stretches out, pushes out. You're damming it up. You have a lot of energy there. The energy does something. It pushes. It pushes. It pushes the material out further, which makes it cooler, which dams up the energy even more, which pushes more, which cools it more, which pushes more. Very quickly, you go from something like this with a little bitty sun, bye-bye Mercury, bye-bye Venus, bye-bye Earth. Very quickly, a few 100,000 years or so, the sun swells just because of this damming up, pushing that material out. And the inner solar system has now been vaporized. Nice thing to know. So, and the whatever habitable zone there was around the sun is now somewhere out here. You know, so Mars doesn't work anymore. You've basically cleaned out the inner part of the solar system. Here's another picture. Same thing. Just giving you the scale of what happens to the sun. Same material. It's just swollen, and there was nothing blew it up except it blew itself up. Energy getting dammed up, causing the push. Well, further things happen, and if I'm teaching a class, you spend a lot of time in the class, but in real time, it doesn't happen. It doesn't last the astronomical time scale, it doesn't last very long, so I'm not going to spend a lot of time on it. The amount of words I use will be proportional to the amount of actual cosmological time that's involved. But the helium in the core gets fused to carbon and oxygen and neon. Somebody asked a question about can you have white dwarfs with or stars that aren't carbon and oxygen? You can have oxygen and neon. white dwarfs, but that's about as far as you can go. What will happen? Well, when helium fusion starts, the star will start getting. Oops, something happened there that didn't want to happen. The star there from the red giant, temporarily smaller, and then much larger again. Very, very large, called an asymptotic giant branch, a second giant branch star. Basically, now Mars is toast as well. It's a big star, very big star, very big sun. Now, gravity is a very simple law. Depends on mass and distance. The gravity at the surface of this big thing is pretty small. Gravity depends on the distance to the center. The center is way over there, the outside is way over there. Gravity is small, so the outsides aren't being held very, very strongly. They're just being held on barely. So that if there's any instabilities, and there are instabilities, there can be extra pushes, extra pulsations, extra explosions, whatever, and the material that's on the outside just starts to come off. This is showing one of the instabilities. It starts to come off, and you saw this animation earlier. Material, it comes off. What's left, all the outside comes off. What's left is the core. That's all that's left. The hot core, which is hot by definition, lights up what just came off, and that's what you call a planetary nebula. I kind of like that because they're useful for a lot of things. It got me a job. Some of the stuff I did with planetary nebulae actually tricked Penn State into hiring me years ago. So here's and there's plenty of pictures of these pretty things on the web. Some of which actually were taken by people in this room. All of these are planetaries. They're very small, faint central, usually faint central star in the center. Actually, not that faint. That's one of the brightest stars in the Milky Way, except that it's so hot, the light doesn't come out in visible wavelengths that we see. It comes out in ultraviolet wavelengths, which is not being taken picture of, blah, 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 blah. More pictures. I throw a gratuitous. Note they're not all very symmetrical. They're very weird shapes sometimes. Where do the weird shapes come from? If I don't ask that question, somebody always asks that in the question and answer, and then I get all nervous and try to make something up. So rather than make up something up in the question and answer session, I'll make something up right now. That you can make these shapes if there's something else around. If the star, if our sun had another companion star, a binary star, or if it had planets. Actually, it does have planets. So just the fact that, say, a Jupiter is going around might be enough to shape some of the ejecta into these strange shapes that you're seeing. And here's an animation that is in one case where you have two stars going around, one about ready to become a red giant, and the two stars merge. One star goes in orbit inside the other star rather than the outside of the other star, and you get a mess that's called a planetary nebula. Just to show that you can get these things. Our sun likely will not be this spectacular because it doesn't have another star orbiting it. It does have Jupiter that might make some of the strange shapes that you saw, but really it's a very complicated problem, one that's too complicated for my little mind, so I don't do those things. And again, more gratuitous pictures of planetary nebulae. Anyway, the end point, well, as Kevin already mentioned, what is left is the core. That where all the nuclear reactions occurred, which were really hot, but now you fused the carbon, there's the oxygen, there's nothing more left, no more fusion left. Somebody turns off the stove, and the stove cools. I wouldn't suggest you touch it immediately. If you want to actually touch it, you probably should wait 10 to 20 billion years until it cools off enough. But eventually, you get a star, a white dwarf, that's about the size of the Earth, that is just cooling, made of carbon, some oxygen, maybe a little neon in there. Electrostatic repulsion prevents any reactions to occur, and this material starts to crystallize over time. And it's very nice to say it crystallizes into a diamond because that's what crystallized carbon is. Although there's more ways to crystallize carbon than just the diamond, so it may go into a different crystallization state, but that shouldn't stop a good story. So, end product of the sun's evolution in about 5 billion years will be one of these guys. A white dwarf star with its ejecta, the stuff that came off the outside, off into space, ready to be collected, gravitationally attracted to something to form a next generation of stars. And that's all I have. Thank you. Yeah, better to eat that than
How can you compare like the whole series of the life of the star to compare it to like say like a match gun scale? I mean, it's the same kind of fusion that happens at a small micro level of a.
It's well, a match is it wants me to make a comparison between a nuclear fusion and say a match going off. And, yeah, it's some kind of explosion. Well, a match is chemical and this is nuclear, so there's that. There's a subtlety involved that in some of these reactions that Kevin avoided because it is a subtlety, that he made it sound like if you bring two hydrogen atoms together, you get a nuclear reaction. And no matter what you do, that will never occur. There's got to be a little bit of magic thrown in. It's called the weak nuclear force, but I like to call it magic, where spontaneously a proton changes into a neutron, and then they can get together. It happens so rare that those nuclear reactions have a thermostat. It just can't go faster than this very rare thing. And so it's much stabler. It's not something like an atomic bomb or something. You get something a lot more stable. If you didn't have this, the whole sun would just blow up in an instant. Boom. And so there is this little magic. The magic happens to be to very quickly to assimilate the magic in your head. You just remember 2, 5, and 8. There are no stable elements with 2 protons, or 5 protons or neutrons, or 8 protons or neutrons. There are no such things, and just trying to avoid that controls all of stellar evolution. That's the quick way. 2, 5, 8.
It seems like your white dwarf is hoarding all the heavy elements.
Yes.
Anything is blowing off is gas.
Yeah, there is in the process. There's a couple of oddities that can occur. you're right. Most of the heavy elements for the sun will get locked up in that white dwarf, so they don't actually make it into space. That's right. There are a couple of odd reactions that occur, and that can mix some heavier elements into the outside, which can get blown off. It's a kind of complicated thing. In fact, when I was in grad school, you could run it on a computer almost as fast as the star would actually do it. The star would do it over time scales of thousands of years. That's how long a computer would take to actually do the calculation, 1,000 years. It's gotten better now, but it's one set of explosions interacting with another set of explosions and mixing things up. And so some heavier elements, principally nitrogen, some neon, some even heavier will actually get thrown out into space, but not a lot.
What would you say is your favorite planetary nebula?
My favorite planetary nebulae. Okay, I can't. Since I work on mostly extragalactic planetary nebulae, I say the ones in Virgo because that got me a job. But as far as NBC 1501, and Howard Bond can tell you it's a seismologist's dream. It pulsates. It does all sorts of things, and I've spent many a night at a telescope. Reading books while the telescope observes the dumb thing.
Sound like a tabby star.
No, it's fairly innocuous, except the star does not stay the same brightness. It gets brighter and dimmer, brighter and dimmer, brighter and dimmer on about 20 minutes, 25 minutes, in a very irregular way.
It's actually doing that, not the 3 around.
No, it's actually doing it. It's like the easiest analogy, the most correct analogy, is earthquakes on Earth, vibrating the star. Right, the earthquake vibrates the Earth, the surface of the Earth. That same type of thing is vibrating the surface of the star, and we can see the star get brighter and dimmer because it's like think of a balloon that's nice and round, but you squeeze now. Put your hands on it, squeeze one side in, the other side pops out, and you get all sorts of weird shapes. Each one changing the amount of light coming out of it from moment to moment.
It's like Robin again.